Good day. This video presentation, we will show you what is thermodynamic cycle is all about and identify and explain how its cycle works. To begin with, what is thermodynamic cycle? Thermodynamic cycle, a process in which fluid includes air, water, ammonia, etc. successively change state from a liquid to a gas and back to a liquid for the purpose of producing or transferring energy. Also, thermodynamic cycle consists a linked sequence of thermodynamic processes that involve transfer of heat and work into and out of the system, while varying pressure, temperature, and other state variables within the system and that eventually return that system to its initial states.
Wendell Bacolod, I will discussing Carnot Cycle, which of the one famous cycle. What is Carnot Cycle? It's an ideal heat engine cycle. In the Carnot Cycle is the theoretical ideal thermodynamic cycle, proposed by French physician Sadi Carnot in 1824 and expanded upon by others in the 1830s and 1840s. An additional composed of four reversible processes. Reversible processes is a process whose direction can be reversed to return the system to its original position. Also is used as ideal gas as working medium. So that is the perfect engine. No friction, no heat transfer. And now, following are the four processes of the Carnot cycle. In letter A, the process of reversible isothermal gas expansion is the process the amount of the heat absorbed by the ideal gas in from the heat source which of the temperature of pH the gas expand is the work of the surrounding. In letter B, the process of reversible adiabatic gas expansion, where the system is thermally isolated and the gas continue to expand and work is done surrounding. Now the temperature is lower T1. And then letter C, the process reversible is the thermal gas compression process, where the heat loss Q1 occurs when the surrounding of the work of the temperature T1. And letter D, the process reversible adiabatic gas compression. Again, the system is thermally isolated. The temperature again rise back to pH to surrounding continue to the work the gas. 1. Isothermal expansion. The gas is taken from P1, B1, T1 to P2, B2, P3 to heat Q1 is absorbed from the reservoir at the temperature T1. Since the expansion is a thermal, the total change in internal energy is zero and the heat absorbed by the gas equal to the work done by the gas on the environmental which is given as the step 2 adiabatic expansion. The gas expands adiabatically from P2, B2, T1 to P3, B3, C2, D2. Step 3 isothermal expression. The gas is compressed thermally from the state P3 to B3 to T2 to P4, B4 to T2. And step 4 adiabatic compression. The gas is compressed adiabatically from the state P4, B4, T2 to P1 to B1 to T1. And now here's the total work done by the gas on the environmental in the complete cycle is a given. Net efficiency. And the last, so the expression for net efficiency for Carnot engine reduced to net efficiency.
Hi, I'm John Andre Ababa and I will be discussing about the Stirling cycle. The Stirling engines can function as work-producing device. This brings a reversible operation flexibility. The source of high-temperature heat can be concentrated solid, biomass combustion, or any waste heat. They are suitable devices for concentrated parabolic dish applications, where the thermal energy can be converted into mechanical energy directly. The Stirling cycle bears a double effect piston and cylinder arrangement. A generator porous matrix is mounted inside the arrangement. The working fluid can be air, helium, nitrogen, hydrogen, CO2, and etc. The main processes within the Stirling cycle. Process 1 to 2, isothermal compression. The working fluid is compressed isothermally while space discharges the heat sink. Therefore, the temperature of the heat sink is increased. Process 2 to 3, isochoric regeneration. Heat addition. Heating occurs at the regenerator under constant volume. The temperature of the working fluid increases from T sub L to T sub H. Process 3 to 4, isothermal expansion. The working fluid expands isothermally while space is heated externally by the heat source. At this stage, the engine produces useful work. Process 4 to 1, isobaric regeneration. Heat rejection. Cooling occurs at the regeneration component at constant volume. The regenerator absorbs heat from the working fluid. The temperature of the working fluid reduces from T sub H to T sub L.
Diesel cycle is a combustion process of a reciprocating internal combustion engine, sometimes it called compression ignition engines because initiation of combustion relies on air heated by compression rather than on an electric spark. Diesel cycle commonly used to model the cylinder of spark ignition, internal combustion, automobile engines, gasoline engines, and etc.
Rudolf Diesel invented the diesel cycle, a German inventor and mechanical engineer famous for invention of the diesel cycle.
1 to 2 is isentropic compression of the fluid. 2 to 3 is reversible constant pressure heating. 3 to 4 is isentropic expansion. To get the formula for pressure, pressure is the force per unit perpendicular area over which the force is applied. So P is equals to F over A. To get the formula for the temperature, temperature is a measure of the average kinetic energy of the atoms or molecules in the system. For volume, the basic formula for volume is length times width times height. Heat rejected is when the insulation of the cylinder wall, the heat transfer through the cylinder walls to the cooling system is reduced, which change the combustion characteristics of the diesel engine. Thermal efficiency is the ratio of net heat output for heating or removal for cooling to energy input or the coefficient of performance. So what is heat added? Heat added fuel is ignited by heat generated during the compression of air in the combustion chamber into which fuel is injected.
Otto cycle is a idealized thermodynamic cycle that describes the functioning of a typical spark ignition piston engine. It is a thermodynamic cycle most commonly found in automobile engines. The Otto cycle is the set of processes using by the spark ignition internal combustion engine, which is the forced stroke. Otto cycle developed by Nicholas Otto in 1876. What are the processes in Otto cycle? We have a PV diagram here. In process 1 to 2, we have the isentropic compression, which the air and fuel ejected after the intake stroke. The air and fuel will compress isentropically. In process 2 to 3, which is the isentropic heat addition, while in 3 to 4, we have the isentropic expansion during the power stroke, when the piston goes in bottom dead center. And lastly, the process 4 to 1, the isentropic heat rejection, in which we have the exhaust stroke. Formula in state properties in temperature. To find T2, we need to use T1 times R raised to the K minus 1. T3, which is the maximum, is equals to T4 times R raised to the K minus 1. While in pressure, P2 is equals to P1 times R raised to the K. P3, which is the maximum 2, is equals to P4 times R raised to the K. And then, in P2 over T2 is equals to P3 over P3. And P4 over T4 equals to P1 over T1. While in volume, volume 1 over volume 2 is equals to volume 4 over volume 3. Followed by compression ratio is equals to maximum volume over minimum volume is equals to volume 1 over volume 2 is equals to 1 plus percent clearance over percent clearance. To get percent clearance, we need to use V2 is over VD is equals to V2 over V1 minus V2. Next is heat addition. We have QA is equals to M air times CB air times T3 minus T2. And heat rejection, we have QR is equals to M air times CB air times T4 minus T1. While in network of the cycle, we have W net is equals to heat addition minus heat rejection. In thermal efficiency, we have 9 is equals to 1 minus 1 over R raised to the K minus 1 times 100%. In mean effective pressure, we have the derived formula PM is equals to W net over VD is equals to W net over V1 minus V2.
I'm Edward and this is dual cycle. Dual cycle or limited pressure cycle is a thermodynamic cycle that combines the Otto cycle and the diesel cycle. In the dual cycle, combustion occurs partly at constant volume and partly at constant pressure. In the dual cycle, the system executing the cycle undergoes a series of 5 processes. 2 isentropic processes alternated with 2 isochoric process and 1 isobaric process. First is the isentropic compression or compression stroke. The gas is compressed adiabatically from state 1 to state 2 as the piston moves from intake valve closing point to top dead center. The surroundings do work on the gas, increasing its internal energy and compressing it. On the other hand, the entropy remains unchanged. The changes in volumes and its ratio B1 over B2 is known as the compression ratio. The compression ratio is smaller than the expansion ratio. Next is the isochoric compression or ignition phase. In this phase, between state 2 and state 3, there is a constant volume heat transfer to the air from an external source while the piston is at rest at top dead center. This process is similar to the isochoric process in the Otto cycle. It is intended to represent the ignition of fuel-air mixture injected into the chamber and subsequent rapid burning. The pressure rises and the ratio P3 over P2 is known as the explosion ratio. Next is the isobaric expansion. In this phase between state 3 and state 4, there's a constant pressure heat transfer to the air from an external source, while the piston is moving toward the V4. During the constant pressure process, energy enters the system as heat and part of work is done by moving piston. Next is the isentropic expansion, also a power stroke. The gas expands adiabatically from state 4 to state 5 as the piston moves from B3 to bottom dead center. The gas does work on the surroundings and loses an amount of internal energy equal to the work that leaves the system. Again, the entropy remains unchanged. Last is the isochoric decompression or exostroke. In this phase, the cycle completes by a constant volume process in which heat is rejected from the air while the piston is at the bottom dead center. The working gas pressure drops instantaneously from 0.5 to 0.1. The exhaust valve opens at 0.5. The exostroke is directly after this decompression. As the piston moves from bottom dead center to top dead center, with the exhaust valve open, the gas mixture is vented to the atmosphere and the process starts anew.
The Brighton cycle is a thermodynamic cycle named after George Brighton that described the working of a constant pressure heat engine. The original Brighton engines used a piston compressor and a piston expander. But more modern gas turbine engines and air-breathing jet engines also follow the Brighton cycle. Air is compressed in the turbine compressor. The air is then mixed with fuel and burned under constant pressure condition in the combustor. That resulting hot gas is allowed to expand through a turbine to perform work. Next one is the PV and TS diagram. In this, you can see the process and the cycle. Is formula of each process. Process 1 to 2, isentropic compression. WC is equals to Cp, T2 minus T1, and T2 is equals to T1, P2 over P1. Gamma minus 1 over gamma equals to T1, Rp, gamma minus 1 over gamma, where Rp is equals to P2 over P1 is equals to pressure. Process 2 to 3, isobaric heat addition. QR is equals to Cp, T3 minus T2. Process 3 to 4, isentropic expansion. Wt is equals to Cp, T3 minus T4, and T3 is equals to T4, P3 over P4. Gamma minus 1 over gamma is equals to T4, Rp, gamma minus 1 over gamma. Wnet is equals to Wt minus Wc is equals to Cp, T3 minus T4 minus Cp, T2 minus T1. Next is the thermal efficiency of Brighton cycle. Thermal efficiency is equals to work output over heat supplied equals Cp, T3 minus T4 minus Cp, T2 minus T1 over Cp, T3 minus T2 equals T3 minus T4 minus T2 minus T1 over T3 minus T2 is equals to T3 minus T2 minus T4 minus T1 over T3 minus T2 equals 1 minus T4 minus T1 over T3 minus T2. Putting value of T3 and T2 equals 1 minus T4 minus T1 over T4 RP gamma minus 1 gamma minus T1 RP gamma minus 1 over gamma. Thermal efficiency is equals to 1 minus 1 over gamma minus 1 gamma RP.
Hi, I'm James Kenneth Trinidad and I will be discussing about the Rankine cycle. The Rankine cycle or Rankine vapor cycle is a process widely used by power plants such as coal-fired power plants or nuclear reactors. In this mechanism, a fuel is used to produce heat within a boiler, converting water into steam which then expand through a turbine producing useful work. A Scottish engineer, Engineer William J. M. Rankine, described and developed the cycle in 1959. This thermodynamics cycle consists of four main steps or components. Isentropic compression is the first step in Rankine. In this process, the surroundings do work on the fluid, increasing its enthalpy and compressing it. On the other hand, the entropy remains unchanged. The work required for the compressor is given by W sub pumps equals H sub 2 minus H sub 1. Then, the isobaric heat addition. In this space, there is a constant pressure heat transferred to the liquid condensate from an internal source. Since the chamber is often to flow in and out, the net heat added is given by Q sub add equals H sub 3 minus H sub 2. Isentropic expansion. Steam from the boiler expands in a steam turbine to produce work and then is discharged to the condenser. The steam does work on the blades of the turbine and loses an amount of enthalpy equal to the work that leaves the system. The work done by turbine is given by W sub T equals H sub 4 minus H sub 3. Again, the entropy remains unchanged. Isobaric heat rejection. In this space, the cycle completes by a constant pressure process in which heat is rejected from the partially condensed steam. There is heat transfer from the vapor to cooling water flowing in a cooling circuit. The vapor condenses and the temperature of cooling water increases. The net heat rejected is given by Q sub RA equals H sub 4 minus H sub 1. This is the formula of the thermal efficiency of the practical Rankine cycle.